There is a way to turn loose sand into solid stone. No heat, no kilns, no cement, no chemical reactions requiring industrial equipment. It happens at room temperature. It happens in 72 hours. And the material it produces is the same mineral that built the pyramids, the Colosseum, and every great cathedral in Europe. The same mineral in seashells. The same mineral in your bones. It has been happening in ordinary soil for hundreds of millions of years. The thing doing it is a bacterium. The question is why you have never heard of it. The archive opens not in a construction site, but in the dirt beneath your feet. Sporosarcina pasteurii has been living in soil, in caves, in lake sediments, and on the ocean floor for hundreds of millions of years. Microbiologists first catalogued it in the early 1900s. At the time, it seemed like nothing more than a strange soil bacterium. Scientists knew the bacterium produced extraordinary amounts of an enzyme called urease, an enzyme that breaks down urea into carbonate ions. Those carbonate ions bind with calcium to form calcium carbonate crystals. They knew this for decades. It was a curiosity. A footnote in microbiology textbooks, a bacterium that did something interesting in a petri dish. Nobody asked what it could do in a construction site. In the 1990s, a soil engineer named Jason de Jong at the University of California, Davis began asking exactly that. De Jong was working on a problem in geotechnical engineering, how to stabilize loose sand in earthquake zones without injecting chemical grouts that contaminate groundwater and require energy-intensive manufacturing. He had read the literature on microbially induced calcite precipitation and wondered if Sporosarcina pasteurii could be injected into unstable soil the way a doctor injects medication into a patient. Not to kill anything, to build something. He ran the experiments. The sand hardened. The calcite crystals formed exactly where he needed them, bridging the gaps between grains, locking the structure in place. De Jong's papers drew immediate attention from the United States Army. The military had a specific problem in forward operating bases in Iraq and Afghanistan. Helicopters kicked up choking clouds of dust and sand that destroyed engines and blinded pilots. Spraying chemical suppressants worked temporarily. They also contaminated soil and required constant resupply. De Jong's bacteria could stabilize a landing zone by growing stone in the sand itself. DARPA funded the research. Field trials were conducted. The bacteria worked outside the laboratory in desert sand, even in 130 degrees of heat. The landing zone hardened. Nobody announced it. Nobody ran a press release. The military uses what works. Here is why the rest of the world should care. Cement production accounts for 8% of global carbon dioxide emissions, more than aviation, more than shipping. Every year the world produces enough concrete to build a wall around the equator and then build it again, and the carbon released in the process is cooking the planet. The bacteria that harden De Jong's sand columns emit none of it. No kilns, no furnaces, no carbon dioxide. The process runs at room temperature, powered entirely by microbial metabolism. That is the scale of what is sitting in a petri dish. And in 2024, De Jong's team demonstrated something that changes the entire picture for civilian construction, and a shelf-stable dry formulation of Sporosarcina pasteurii. Bacteria preserved and packaged like a powder. No fermenters, no mobile microbiology lab, no cold chain. A contractor opens a bag, adds water, and within 24 hours the bacteria are producing calcium carbonate in the field. The single biggest barrier to real-world deployment, the need to bring a laboratory to every job site, is gone. A bag of bacteria, add water, wait 24 hours, the sand becomes stone. To understand what Sporosarcina pasteurii actually does, you have to understand the chemistry it runs. But the strangest part isn't that the bacteria make stone, it's how they do it. The bacterium produces extraordinary quantities of an enzyme called urease. Urease breaks down urea, a nitrogen compound found in soil and urine, and releases carbonate ions. When calcium is present in the surrounding solution, those ions bind to it and form solid calcium carbonate, in other words, limestone. The crystals form preferentially at nucleation sites. Sporosarcina pasteurii has a specific advantage here. Its cell wall carries an exceptionally strong negative charge which attracts positively charged calcium ions and makes the bacterium itself a nucleation site. The cell becomes a seed crystal. Limestone grows directly around it, encasing it in stone. Think of it like mortar between bricks, except the mortar is grown, not mixed, and the bricks are individual grains of sand, crystal by crystal, contact by contact. Loose sand that pours through your fingers becomes a load-bearing solid. The compressive strength achieved depends on how many treatment cycles are applied, meaning how many times the bacterial solution and calcium source are injected or percolated through the sand. In laboratory studies at the University of California, Davis, sand columns treated with microbially induced calcite precipitation have achieved compressive strengths exceeding 10 megapascals, comparable to soft sandstone, and in the range required for structural applications. Standard Portland cement concrete achieves 20 to 40 megapascals, so biocemented sand is not a direct replacement for high-load structural concrete, but for ground improvement, foundation stabilization, erosion control, and applications where you need sand or soil to stop moving and start bearing load, it is more than sufficient, and it is achieved without a single degree of added heat. A bacterium that can stabilize foundations, harden desert landing zones, and bind architectural tiles, yet almost no one outside engineering labs has heard of it. At this point, the idea sounds almost unbelievable. So scientists tried something simple. They poured the bacteria into a column of loose sand. They added calcium and urea, and they waited. Days later, the column was solid. The first person to take this out of the Geotechnical lab and into architecture was not a soil engineer. She was a woman who grew up collecting seashells on a beach in Alabama. Ginger Krieg Dossier was an architect. In 2006, working in the United Arab Emirates, she looked at the scale of construction happening around her, buildings going up on every block, concrete being mixed by the thousands of tons. And she started thinking about calcium carbonate. A seashell is calcium carbonate. It is harder than most ceramics. It is grown by a living organism at sea temperature, without heat, without fossil fuels, without a kiln. She began researching the organisms that produced it. She found the literature on MICP. She found S. pasteurii. After 111 failed experiments, Dossier grew her first brick. She packed sand into a rectangular mould, inoculated it with bacteria, and introduced calcium and urea. Over 5 days, the bacteria grew calcium carbonate at every contact point. The sand solidified. She removed the mould. The brick held its shape. It had compressive strength comparable to fired clay brick. It had been made at room temperature. It had produced no carbon dioxide. She moved back to the United States and in 2012 founded Biomason in Raleigh, North Carolina with her husband Michael. Their first commercially available product, BioLith, is a precast tile made from 85% recycled granite aggregate and 15% bio-cement. It is in commercial production. It is being used in buildings in parallel. Biomason signed a contract with the United States Department of Defense to develop engineered living marine cement. Bio-cement seeded with marine microorganisms that source nutrients directly from seawater to propagate calcium carbonate structures with self-healing properties. The same bacteria that De Jong used to stabilize helicopter landing zones are now being used to grow structures underwater that repair themselves. Dossier's goal, stated plainly, is to reduce 25% of carbon emissions from the global concrete industry by 2030. She is not speaking metaphorically, the production is running, but Biomason's tiles are not replacing Portland cement, not yet. And to understand why, you have to understand what it costs to grow stone. There is one limitation worth naming, honestly, before going further. The urea breakdown that produces carbonate also produces ammonia. At construction scale, this matters. Ammonia in high concentrations is toxic to aquatic life, and unmanaged ammonia release at a field site creates the same environmental problem that chemical grouting does. Researchers are working on it: zeolite adsorption to capture ammonia, substitution of urea with sodium bicarbonate, and process redesign that reduces ammonia release by up to 75%. The problem is real. It is being solved. But anyone who tells you microbially induced calcium precipitation is already a clean zero waste process is running ahead of the current science. Dossier knows this, De Jong knows this. The honest version of the story includes it. The cost is the other central problem. Portland cement costs roughly $100 per tonne. Current biocement production costs are higher, significantly higher, because the bacterial growth media, the urea and the calcium chloride, all add input costs that Portland cement's simple limestone and heat formula does not carry. Researchers are working on cheaper alternatives. The cost curve is moving downward. It has not yet reached parity. The building codes do not recognize biocement as a structural material. There are no ASTM standards for microbially induced calcium precipitation, MICP, treated soil or biocemented aggregate. An engineer who wants to specify it today would be writing in a language the code does not speak yet, which means the insurer will not cover it, which means the contractor will not risk it, which means the default is Portland cement every single time. This is not a conspiracy, it is bureaucratic gravity. Standards take time, testing programs and industry consensus. The testing is happening, the consensus is forming, but it is forming slowly. The cement industry produces 4 billion tonnes annually. It employs millions of people. It is embedded in the supply chains of every construction project on Earth. It does not need to suppress biocement, it simply needs to wait. That process is underway. It is not fast. It was never going to be fast. What is already happening today is worth paying attention to. Jason De Jong's group at UC Davis has spent 30 years moving this from laboratory columns to field scale. Soil slopes, earthquake test sites, desert landing zones, the work crossed every threshold the critics said it would fail at, and kept working. Magnus Larsson's conceptual Sahara Wall, the US Army Corps of Engineers dust suppression trials, and Biomason's biolith tiles in real buildings all prove the same thing. The bacteria are already building. There is a bacterium that turns sardine into stone. It needs no heat. It releases no carbon dioxide. It has been doing this since before the dinosaurs. The science is done, the production is running, the powder is in the field. The building codes will catch up. Portland cement will not disappear for the highest load applications. Skyscraper cores and major bridges still need its strength. But for ground stabilization, erosion control, foundation improvement, dust suppression, marine structures and low carbon tiles, biocement is not a future technology. It is a present one. The question the construction industry is currently trying to answer is not whether the bacteria can grow stone. They can. They have been doing it for longer than we have existed. The question is how fast we can get out of the way and let them. So why haven't you heard of bacteria that turn sand into stone? Because industries that produce 4 billion tonnes of material every year don't change overnight. Building codes move slowly, standards take decades, and technologies that challenge the foundations of construction often begin quietly, in research labs, in field tests, in small companies experimenting with materials that the rest of the industry isn't ready to name yet. But the bacteria don't care about building codes. They have been turning sand into stone for hundreds of millions of years. They were doing it before the first human mixed the first batch of mortar. They will be doing it long after the last Portland cement plant closes. The question was never whether they could. If you work in construction, geotechnical engineering or materials science, or if you know someone who does, look up De Jong, Dossier and Biomason. That is how this knowledge survives.